Here is another CPU scheduling algorithm, the shortest job first algorithm. The way this scheduling works is, this algorithm for each process estimates the length of its next CPU burst. When the CPU is available, it is assigned to the process that has the smallest next CPU burst or the shortest next CPU burst. In case multiple processes have the same next CPU bursts, then FCFS scheduling is used to break the tie. So out of the processes that are in tie, the one that arrived first would be allowed to go first. Note that SJF for short or shortage of first is also a non-preemptive scheduling algorithm. Once the CPU is given to a process, it will only be voluntarily released by the CPU when the CPU burst completes. Let's try to understand the workings of shortest job first or the SJF algorithm better with the help of this example. For simplicity, in this example we are going to assume that every process has just one CPU burst. There are four processes, P1, P2, P3 and P4, and their CPU burst times are as given in the table here. So this is the burst time. P1 has a burst time of 7 milliseconds, P2 has 4 milliseconds, P3 has 1 milliseconds, and P4 requires 3 milliseconds of CPU burst time. As a change, note that not every process here is arriving at time 0. The arrival times are indicated in the second column here. So P1 arrives at time 0, but P2 arrives at 2 milliseconds, P3 arrives at 4 milliseconds, and P4 arrives at 5 milliseconds. So given this information, let us try to complete the Gantt chart here for this for this SJF scheduling algorithm corresponding to the given set of processes. So here at time 0, only process P1 would be present in the system. So there is no choice because there is only one process. This process has to be scheduled. So P1 gets to execute starting time 0, and it requires its burst time is 7 milliseconds. So it will finish here at time 7. So P1 executes from time 0 to 7 milliseconds. In the meantime, note that P2 will arrive at time 2 milliseconds. So here at 2 milliseconds P2 arrives, and P3 will arrive at time 4 milliseconds. So P4 arrives here at 4. And I'm sorry, P3 arrives at time 4 and P4 arrives at time 5. So P4 arrives here. So at time 7, P1 has finished. Now the CPU is free, so we have to pick one of these P2, P3 and P4 as the next process to execute. So for the shortest job first, we'll look at their burst times. Note that, and we'll pick the one that has the shortest CPU burst. So note that P3 has a CPU burst of 1 milliseconds as compared to 3 milliseconds of P4 and 4 milliseconds of P2. So P3 has the shortest CPU burst, therefore P3 gets to execute next. So we'll give the CPU to P3 and it will take 1 millisecond to execute. So it will start at time 7 and it will finish here at time 8. So here P3 finishes. So now P3 is done too. Next, we need to pick either P2 or P4, which are the remaining processes to schedule on the CPU. So P2 has a burst time of 4 milliseconds and P4 has a burst time of 3 milliseconds. So the shortest of first would pick P4 as the next candidate. So P4 will start executing here at time 8 and it has a burst time of 3. So it finishes at 8 plus 3, 11 milliseconds. So P4 executes next and finishes here. And finally, after P4 has finished, P2 will get to execute next, and P2 requires 4 milliseconds, so it will start at 11 and will finish here at time 15. Let us complete this table over here using the information in this Gantt chart. Let's first work on this termination time column. So note that P1 finished here at time 7, right? So the termination time for P1 is 7. P2, note that it finished here at time 15. So termination time is 15. P3, it finished here at time 8. So the termination time of P3 is 8, and P4 similarly finished here at time 11. So that goes here. Next is the turnaround time. Recall, the turnaround time is basically the time that elapses from the beginning of the process to its end. Essentially in this table, the turnaround time would be the termination time minus the arrival time. Therefore, the turnaround time for P1 is 7 minus 0. So that would be 7 minus 0, which is 7 itself. For process P2, it would be 15 minus 2. So 15 minus 2 is 13 milliseconds. For process P3, it would be 8 minus 4. So the 8 minus 4 is 4 milliseconds. And for process P4, it would be 11 minus 5. Right? So 11 minus 5 is 6 milliseconds. And finally, we need to compute the waiting time. Recall, the waiting time is the time that a process spends waiting for its turn to execute on the CPU in the ready queue. Now, in this case, the waiting time would simply be turnaround time minus the burst time. Because recall, in our examples, the processes either execute on the CPU or they are waiting for their turn to execute in the ready queue. So the burst time indicates the time that a process executes on the CPU. The turnaround time is the total of the time the process is spent executing on the CPU and the time it's spent in the ready queue waiting for its turn to execute. Therefore, the waiting time is turnaround time minus the burst time. So let's do this. Process P1, the waiting time would be the turnaround time, which is 7, minus the burst time, which is also 7, right? So 7 minus 7 is 0. For process P2, it would be 13 minus 4. So 13 is the turnaround time and 4 is the burst time. So this would be 9 milliseconds. For process P3, it would be 4 minus 1. So 4 minus 1 is 3 milliseconds. And similarly for process P4, it would be 6 minus 3, which is basically again 3 milliseconds. So based on all of this information, let's now compute the average waiting time for all the processes. So that would basically be simply an average of all these waiting times in the last column. So that would be 0 plus 9 plus 3 plus 3 divided by 4, because there are 4 processes, which is basically 15 divided by 4, which is essentially 3.75. The answers are also summarized over here.